Thank you, Igor. This is Tomoyuki Ichiba. I'm a moderator of this talk. And so let me introduce the speaker today. Professor Sircar is a Eugene Higgins Professor of Population Research and Financial Engineering at Princeton University, and is affiliated with multiple places, Penn Center for Finance, the program in Applied and Computational Mathematics, and Erlanger Center for Energy and Environment. His research interest centers on financial mathematics, stochastic volatility models, energy markets, and exhaustive resources, credit risk, asymptotic and computational methods, portfolio optimization, and stochastic control programs, and stochastic differential games. He is a co-author of the book Multiscale Stochastic Volatility for Equity, Interest Rate, and Credit Derivatives, published by Cambridge University Press in 2011. And was founding co-editor-in-chief of the SIAM Journal of Financial Mathematics from 2009 to 2015. He was made a fellow of the Society for Industry and Applied Mathematics, SIAM, in 2020 for contributions to financial mathematics and asymptotic methods for stochastic control and differential games. So Professor Sircar, could you share your screen, your talk slides, and
okay, will do.
Thank you.
Thank you, Tomoyuki, for the introduction. Let me just start this.
Participants, if you have questions during the talk, write your questions, comments in the chat box, and I will take your questions.
Okay, so
thank you.
So thank you for the introduction. Oops. All right. So I'm trying a new technology here, which is acting up. Okay, not going well. All right. So okay. So yes, thank you. So this is slightly different from the usual type of thing that I might present at this thing. So I gave this sort of James Bond title, Orpheus, and what this stands for is written here. It's a mouthful, but it was just to get the acronym. And so this is to describe a project to do with risk management of the electric grid in the presence of increased renewables, which is part of a big team, including SPIs, myself, and Rene Carmona at Princeton, Mike Lukowski, who's on this call at Santa Barbara, and Glenn Swindle, who works for who runs his own firm, Scoville Risk Partners. And then there is a bunch of postdocs and software engineers and so on involved in this. And what I want to present is one part of this project. And most of this was done with Mike Jankowski, who's a research software engineer, and Arvind Shrivats, who I think is on the call, is a postdoc at Princeton. And the rest of the team is at this website that is listed here. Okay, so okay, so here's the problem. You know, many people obviously are aware of this issue that is increasingly discussed, that you know, we are and plan to use more renewables for electricity production going forward to reduce carbon emissions, and a lot of states have committed quite aggressively to you know, a certain percentage of renewables in the mix. And when I say renewables for this talk, I'm mainly dealing with solar and wind production. There are other things, hydro, etc., but I'm not going to deal with that. You know, so this is to complement production from natural gas, coal, nuclear, which are the traditional or conventional, I'll call them, sources of production of electricity. Now, you know, one of the issues is that you know, once you've built a solar or wind, essentially to produce electricity from them, the cost is you know, is effectively zero, whereas on, you know, natural gas now, for example, is very expensive because prices of the fuel are very expensive. They have more substantial operating costs, et cetera, et cetera. And so the part of the electricity market that we're interested in to start with is this day-ahead market. So the night before in the US, the night before the electricity is dispatched to the utility companies, which then goes to your homes and offices and so on, there is this market, and these producers bid a certain amount of electricity that they are willing to produce for each hour or 15 minutes in the 24-hour period ahead, and at what price they're willing to supply that electricity. And renewables essentially can bid at zero, whereas natural gas and so on have to cover their costs, and so they are higher up the so-called bid stack. And then there is some sort of market clearing procedure, and one price essentially, I'm simplifying it a little bit, is set for each, let's say, hour every day. And people who bid below that price, will be called upon to provide electricity. People who bid above may not be called upon. Okay, and so there may be natural gas or conventionals which bid, but given so there is a supply-demand curve I don't put here. The demand, we assume we know what the demand for electricity is going to be on the next day, and some conventionals, natural gas units will not be turned on because they're not forecast to be needed the next day. That things can be covered with renewables and some other conventional sources. But the problem, and this is a new and growing problem, is that renewables are inherently intermittent. So the sun goes behind the clouds, the wind drops unpredictably, and so as we go more and more renewable, the problem is that this uncertainty cannot be ignored, and a lot of this whole project is funded by something called ARPA-E, which is an agency under the Department of Energy, which is obviously concerned that this is going to be a problem that has to be addressed and has to be quantified. And the goal of this sequence of projects, and there's our team, there's other teams at various universities as well, is to try and bring some sort of financial perspective to it, in particular stochastic and statistical modeling, to try and quantify, put numbers on this issue about unreliability. The other thing I will stress is that, at least from what I've learned of how the power grid, power systems, the engineers and so on who work in this, it's almost entirely deterministic. And that's been kind of okay because demand is somewhat predictable, and you didn't have this level of uncertainty that we're going to have now, and we're going to see increasingly in the future. Okay, so this is the problem. And so this project, which is a 3-year thing involving a bunch of people, has various aspects. And so most people here are familiar with how we think of stochastic modeling in financial mathematics and engineering. You do a statistical analysis of the data, you produce a stochastic model, you maybe do simulations if you can't compute things effectively, and then there may be some optimization if you're hedging or portfolio optimizing and so on. So there is this statistics, stochastics optimization way of viewing what is done in a lot of financial engineering, and what is the analog of that here, or so the first part of the project, which was the first year, was essentially to take historical data. So there is data produced by national labs and so on of like existing solar units and wind units and how much they produce. And in particular, the key issue is that there is a forecast of how much sun there will be tomorrow, how much wind there will be tomorrow. And what is the uncertainty is what is the actual production of solar and what is the actual production of wind. So the statistical analysis is of the error between the forecast and the actuals. So this is a part that's been done. I'm not going to talk about that. These are various people, Rene Kamono, Glenn Swindle, and Shinshiro Yang, part of this team, who worked on that and produced software that we can get Monte Carlo simulations. And that's what we need to be in business about risk measurement, risk management, etc., and to use stochastic methods. So let's take as given that we're at this point and we can, for a certain grid that I'll describe, simulate thousands of times what could happen. Days where it's more sunny than you expect, days where it's less windy than you expect, all kinds of things that are calibrated from historical data, as you would do if you were, doing stochastic volatility models or something like that. Okay, now the part I want to describe is going towards the financialization part, which will be the ultimate, probably, output of this in year 3. So what I'm talking about is kind of this year, what we're doing in year 2. Now, what does the grid operator do? So the grid operator. So what I'm talking about here is, maybe I'll switch to, where is it gone? Hold on, somewhere to write. Okay, so I'll switch to this for a second. So there is an ISO, independent system operator, and these are divided not kind of by states. So there's New York ISO, California ISO, the one you probably heard of if you just followed the news from last year's blackouts is ERCOT, which is most of Texas. In fact, all of the parts of Texas that blacked out. And various other things, who do this auctioning process, who decide the day ahead how much electricity they're going to supply, where they're going to get it, and the constraint, of course, is that the lights cannot go off. So it's not that you raise the price if the demand goes up and some people don't buy. It's demand has to equal supply. So essentially they are solving. They're solving some optimization problem. Okay, and so I don't know. Let just write it in this way. So there are things that are let's just call them X, which are unpredictable, which are stochastic. Okay, but they treat them as predictable. So in some sense, what they're doing is solving a deterministic optimization problem, where this expectation is forecasts, and they assume the forecasts are the actual. That's the shortcut that we've used for 50 years. And then most of the time, the X was demand. But now in this X, I want to put solar production, wind production, etc. But then, if the sun doesn't shine, then you're not going to meet the demand. So the constraint is that the supply equals the demand. Okay, and the theta is the commitment, how much electricity how many, who you turn on, who you call upon, etc., etc. And so this is a very complicated mixed integer program with transmission constraints, Kirchhoff's laws, physical constraints, congestion. It's a thing that's been developed at least since the 80s from people in MIT. There are commercial softwares that do this optimization problem, produced by GE, Siemens, ABB, that they lease to these ISOs for millions of dollars, et cetera, et cetera. And now, of course, people know in this audience that what you should, of course, be doing, and then people know this everywhere, is not minimizing the function of the expectation, but minimizing the expectation of the function. Okay, that's the at least better thing to do. But what I haven't told you is, what is this F? This F is sort of the costs to the system of producing electricity on this day or at this hour, right? And that to go from here to here, very influential people have campaigned for this for many years. And first, the stochastic optimization at the bottom is very what should I say? It's very complicated to have algorithms. And these are huge systems. I'll describe the computing, but essentially it will take, if not an act of God, an act of Congress at least, to change the system. So in coming into this to do something that has any chance or has some chance of being adopted, this thing is gospel. You cannot touch this black box, as we call it, which solves this optimization problem. So you can propose much better things that take into account the stochasticity in an appropriate way, but it won't get off the ground, is the impression that we got. And so in some sense, this black box, min f over theta, this is untouchable. While we don't have access to the commercial version of this yet, we have academic things which we can use. And that black box, although we tinkered with it, what it actually does is not change. So instead of what shall I say? Instead of doing a stochastic optimization, then you feed this with Monte Carlo simulations, and you get some distribution of the risks, and then do risk measurement or risk management or whatever on that. So that's our, that's our approach, because we cannot change that black box in some sense. Okay, so let me go back here. And so what our software, which is an adaptation of somebody else's software, because this is not our expertise, is called Vatic. And that is an adaptation of this other person's software, which is called Prescient. And Vatic, I think, is potentially the same root word as Vatican, but that's not clear. But this is a software in a high performance computing environment, allows parallelization, which is important, of course, to have any chance with Monte Carlo. So, and then, going forward, we want to come up with these simulations and say, the idea is not to say that solar is bad, wind is bad, but to quantify, kind of like credit risk, put ratings on, this solar is not as reliable, that solar is very reliable, et cetera, et cetera. So we want to get out of this, huge simulation exercise, a measure of risk, first of the whole grid, and then top down to the individual units. And so this is, the kind of the mathematical complexity is this risk allocation problem, which people may be familiar with from 20 years ago, when you had the risk of a bank, and you wanted to know which desk did it come from. So the VAR, let's say, of JP Morgan, but how much goes to the foreign exchange, how much goes to or how much comes from the foreign exchange, how much comes from the equity. That's a problem that people have considered over the years, but it's computationally very complex, as I'll say a little bit about. And then the part that we haven't got to, and this needs a lot of thinking, is, okay, so then suppose we have measures of reliability, you have the analog of credit scores. How do you transfer this risk? How do you ensure this risk? How do you, what do? Do you use it to incentivize new renewables plants because what we have is not enough, et cetera? So that's next year in some sense to think about that issue. So I won't talk about the financial side of this because we haven't got there yet. Okay, so this is we have tons of these kind of pictures because we have to present to people who are looking over our shoulders with the checkbook. And so, this is essentially what I described. I don't think I'll go through this picture in the interest of time. And so I think I've already said this, that, one, financial way of thinking is that one way you could think of it is, you have the top down, you have the risk of the CDO, you have the price of the CDO, and you want to, inform the individual units risks with that. So this is essentially top down. It's not that we take the risk of each of the individuals solars and aggregate it into the thing. We see what happens to the grid. Okay, so I'm going to consider this risk allocation in the context of a single day. And how do I sort of measure how much comes from you, how much comes from me? In some sense, this is what people have thought about, is like, what would the risk be if I wasn't there or you weren't there? That might be the first kind of perturbation that you would think of. But here I'm going to say, or we're going to say, or what we landed upon was instead to idealize. Like, what if, I'm an unreliable producer, but I run simulations where I always meet the forecasts, right? So I'm idealized. I'm this perfect world situation, and compare, what happens if I have no risk of underperforming versus, what the actual risk is, and from there to get, use that as a measure of the, of the risk that I'm contributing to the grid. Okay, so again, so these are kind of sort of simplistic versions of what we're, what we're trying to measure. Okay, so the total system cost means how much does it cost the grid to produce electricity on a Monte Carlo run for a given 24-hour period. Okay, and so, these come from various things. They're fixed and variable costs. There will be, penalties for lost load. Like, so if you have to, if you don't meet the demand in certain areas, there's a penalty that could occur in the software. So again, all of this comes from this is not ours essentially, but the model of the grid is Prescient, which is produced from Lawrence Livermore National Labs, but which we've adapted and streamlined into this code that we call Vatic. But the model of how the grid functions is from them. And so for us, the total cost is comes from the fixed cost to run the thing, the variable costs, depending on what happens, and a penalty for load shedding, which sometimes occurs on the Monte Carlo simulations where you can't meet the demand, or you have to go out of state to meet the demand. Okay, and there's some penalty parameter lambda I won't worry about. And so this is about risk management, risk measurement, and so we're worried about days where solar and wind underperforms and the cost is very high. So we're worried about the right tail distribution of the risk to the grid. And so first, now, with RPE, and the reason I'm setting this up computationally is that they're not interested so much in academic studies. That was very clear. They don't want so-called 12 bus systems, little academic things that we can do. They want something that kind of scales to something that's realistic, the size of Texas, the size of New York. Now, you're doing Monte Carlo simulations, you have to do this huge optimization problem. This is a huge computational burden. So to start with, there is a test grid, which is in between an academic toy model and a real grid. It's a fictional grid in Southern California and Southern Nevada. And it's called RTS GMLC, that was developed by who I forget, by National NREL, I think. So I'll consider this first because here we can run a Monte Carlo simulation in 1 minute, and then I'll get to a real grid, which is Texas. Okay, so this is a test grid constructed. I mean, it's realistic but not real. So it's constructed. It has 3 zones. It has 73 load buses, so these transmission nodes that the electricity goes through. And in terms of the renewables, PV is photovoltaic, stands for meaning solar. RTPV is rooftop photovoltaic, so rooftop solar. So there's a distinction between a solar plant and the thing that is on the top of your house, and then there are wind assets. So there's 25 solars, 31 rooftop solars, and only 4 wind. And the kind of time period we're talking about is like 2017, 2018 in terms of this grid. Okay, so here is the output. So there's 1,000 Monte Carlo simulations from things that are calibrated in some way to this grid, even though it's fictional. There's things that you can do, and so this this risk distribution shows there are 2 histograms here. So gray is the original grid. So that means that you run the simulations, you have a set of forecasts, and you see what the cost is for. Okay, so the data is from 2018, but this is run for a date in 2020 using forecasts for that. I think I'm saying that correctly. So so you see that you have, for the gray, you have a wide distribution of costs, and you have kind of a pronounced upper tail when, so high is bad. That the cost of producing electricity on that day was, on some Monte Carlo simulations, very high. And what is changing on those simulations is solar and wind production, essentially, maybe demand as well. But this is really about, and that tail is really coming from uncertainty from solar and wind. And then the red is the perfect world where solar and wind do what they want to do, and of course you have a much tighter distribution because you've taken out essentially the uncertainty, except for the uncertainty in demand. So you have less of a tail risk when renewables are idealized, but you can't quite see it on this graph, but the average cost may be higher. Okay, so this is the kind of simple first look at what happens if it's stochastic and if it's not stochastic. So that's as you'd expect. That's in the summer. This is a winter day of the same grid, and the reason it looks like this is because there's a rather this is winter, so there's a rather large weather-dependent demand, and solar, you can't count on solar so much, but we count on it somewhat. So there's a much larger tail here when the grid is not idealized. Okay, so that's the first kind of sense, hopefully, of what's going on. And now the kind of the risk management part. Okay, so there's a histogram there. From that histogram, you can take a risk measure. And then, as I've said, this has to be allocated back to those 25, 25 solars, 31 rooftop solars, 4 winds. Who can, who is responsible for that right tail? How do you allocate that distribution back? And so, okay, so this is the methodology that I want to describe. And now, even on this grid, the computational burden will come into it. Okay, so here's what we would like to do, and then I'll say what we are able to compute. So, what we are measuring is the difference between the costs of producing electricity on a grid where gray here is BAU, business as usual. So just we didn't tinker with anything, and red is perfect world, PW, which means what is how much more does it cost? X is how much more does it cost in the normal grid compared to when you idealize things. So basically the difference between the red and the gray, or the gray and the red histogram that you saw before. And we run Vatic with the Monte Carlo simulations, let's say 1,000 times, so you get the histogram. That's where we are, what we've shown, and then from that, let's choose some measure of that tail, that right-hand tail. Okay, and so there's a whole literature, of course, on risk measures, and at some point we just have to choose one, and this has to kind of sell in some sense. So the one we thought people know the most in various different industries and so on is CVAR. Okay, so I'm going to take this conditional value risk, which is, this is the formula. This is the formula. I hope it's written correctly, but it's for the right tail, not for the left tail. It's and we're going to take the parameter here is alpha, which is going to be in our experiments 5%. So the 5% tail risk, the integral of the var is the CVAR, or I'm going to assume everyone knows what var is, and probably more useful is to write it in this form. The CVAR at level alpha of a random variable x is the expectation of x conditional, and I may have the inequality wrong here, but anyway, whatever it is for the tail risk being on the other side of the var alpha. Okay, so this is this is the risk measure, and this is, of course, now the measure of the risk for the whole grid. So that's easy to compute from the histograms that I showed you before. Okay, so that I think that's I've said that already, so I don't need anything here. Okay, I think this is, we don't decide that this is easy to understand so far, but this is now the challenge. So now I have the system risk. It's a coherent risk measure, so it's a monetary risk measure, so it's a number in dollars. Okay, that's important, and that dollar amount has to be allocated across these across what? So ideally, I would want to say for each solar unit, for each wind unit, etc. But you might say, okay, maybe I want to do it across zones in the state, or groups, or whatever. Okay, so we'll come back to practically how we do it. But I need to decompose this random variable x into random variables phi, let's say corresponding to each generator. So each rooftop solar, each wind. Okay, and so from those random variables, I need to extract for each unit a dollar amount AI, so that the rho of x, this thing is distributed. So in other words, the risk of the system is the sum of the risks I allocate. Okay, that's nothing nothing major. So everything has to be allocated. Let's say the risk was $2 million. Not the risk, the cost of producing that has to be allocated back. Okay, and so this is then the risk allocation problem. This has been studied, and there is a way that people have proposed that we're just trying to implement of doing this. So just as with risk measures, I don't have this kind of stuff on the slides, but there is there are some axioms for risk measures that you like, convexity, monetary, etc., scaling, and so on. And there are, when you go to risk allocations, there are analogously, axioms that people have proposed. And I don't have references on these slides, but I'm happy to say those at the end. But and then it gets more complicated. There are mathematical things that you might want, differentiability in some sense. There are economic type properties that you want, and so there's a host of candidates of ways to do the risk allocation. One is called the Euler method, but what we're going to adopt for various reasons corresponding to what axioms we thought were important is the Shapley value, which people may have heard of in other contexts. So that's illustrated here. It's written quite simplistically, but let's say you have two groups of assets, or even two. Let's just say two or two groups, right? So I have to allocate some amount X between between two groups of assets. So here the new in gray is the risk to the grid. The gray histogram is its density, and the red is the red histogram. Okay, so X is the difference between those two, as we've said before. Okay, so this is just notational. So this risk, which is the difference between the costs in business as usual in a perfect world, you can add and subtract various things. So you can add and subtract. You can add and subtract the risk of idealizing A but not B, and the risk of idealizing B and not A. And so then you have to, so here it's subtracted, here it's added back. And so you can decompose it, into this thing. And then you can interpret the top line, let's call it phi nu A and phi nu B. So phi nu A is this, the top four things. And this is phi nu B. So X is the sum of these two things. And what we claim is, so in this two asset thing, this is very simple. Those phi's are the phi's for the ways to decompose the random variable. So there's a way to think about it is in this two system case, you can two unit case, you can visualize it as how to get from here to here. Either you go across and down, or you go down and across. One way is that you idealize B. The orange arrow is idealizing B but not A, and the blue arrow is idealizing A but not B. And you want to get from the top left to the bottom right. So averaging across those two is what leads to this decomposition. And then in higher dimensions, you also have this interpretation where you have the hypercube, and you can think of it in those terms if you want. Okay, and so now, okay, so that's with two, and so you can see that it's there was 8 terms or something in that decomposition, and so those phi A and phi B correspond to the Shapley decomposition for these two units. But when there is whatever the number is, m players, m units, then the Shapley value is 1 over the number of players, and then the sum of the marginal contribution of player I to a coalition divided by the number of coalitions excluding I of this size, but here summed over all coalitions. So in other words, this is like where you take each individual asset, you idealize it, then you do it in pairs, then you do it in groups of 3, and you have to contribute, you have to compute this fraction, to each time. So in computing this fraction, this itself is a run of that optimization software, and then the number of coalitions when you have m assets is exponential in m, and so you have the Shapley formula, which is okay for 2, maybe 3, maybe 4, but higher than that, and given that the thing that you have to compute is this enormous thing, is not workable. So here the theory gets stuck because this formula has all kinds of properties in terms of risk allocation, desirable features, etc. I didn't really get into, but it's not tractable computationally for something where the computation of the thing is itself involved. So we have to so here's a little bit more of the theory. So what you can show, so that was decomposing the random variable, and then from that you get the dollar amount that you assign to each of the assets, and that's the expectation of that decompose of player I's random variable, again conditioned on x being on the correct side of the var level for the upper tail. And so of course now you can see, of course, you sum the AIs, you get back to the x, you get back to the row of x that you have. Okay, so all of that makes sense, but it's computationally very involved, as I've said many times. But this is what we choose to try and implement. So here it is again. I say we have lots of these pictures. I don't think there's anything new here. So the total system costs and the total risk, the risk measure of the histogram. So there is something here that I'm going to group the assets in certain groups by type for the purpose of this talk. And I think we're going to choose 4 groups because this is manageable. And so I'm going to allocate the risk into these 4 groups, okay? And then choose what has to be ultimately an ad hoc method. So there's 2 ad hocs. One is how do I group the assets, and 2, within each group, I know the risk allocation, the cost allocation to that group. How do I give those individually? Okay, and then there are checks to see if we did it in different ways, is it robust, etc., which I won't get into here. So okay, so I think this just summarizes everything I have said. So the key thing is that we create these groups, which are here called cohorts of these assets, and what we're going to do is cohort them by the type. So rooftop solar, and wind. These are our results on this RTS grid from a few months ago, but more recently we can run this on a more realistic grid, which is called Texas 7K meaning 7,000 buses. But on the RTS, at least to see what kind of thing you get out of this, we can see from here. So again, I've said, there are choices to be made here to, and how you choose the cohorts. I'm going to do it by, as I said, by the type of unit they are, solar, wind, etc. And then describe, okay, these are a little bit repetitive, how to allocate them back to the asset level. Okay. You want so this side I've said you want the number of cohorts to be small because anything above 4 or so, you're into 2 to the number, etc. And then that's on top of Monte Carlo. Okay. And so just in the interest of time, I think I can skip that. I think, so let me get to the results. I think people understand, or hopefully I've said everything that is going on. So, here is a result for this day, okay, summer day. On the 4 pictures on the left, going on the x-axis is the hour of the day. So 0 is midnight, and on the right of the graph is 11 p.m. to midnight at the end of the day. So let's at least first see if this sort of makes sense. So, this is the output by type, okay? So the gray is the total risk allocation. So this is varying through the hour. Okay, so not much risk in the middle of the night. More costs to produce during the day. So this, this is like the daylight hours. Okay, when solar is underperforming, there's a spike kind of at around what is that, 7 p.m. or 8 p.m., something like that. And we want to see where that comes from. So what this first picture. So there is another uncertainty, which is the load, and so this is just showing the forecast of the load, and I think the band is the interquartile range of the Monte Carlo simulations, and so you sort of see that the forecasts, there's not on this grid too much uncertainty coming from the load, but when you look at, let's say, the wind, you look at the solar and the rooftop solar, then the story is a little bit different. And so you can see the dots there, the Monte Carlo simulations in the tail, I think. And so, those are quite outside the interquartile range. And you can see the band, the pink band, is the, potential disparity from the, from the forecast, which is the yellow thing in the middle. Hopefully you can see that. Okay, so there is a disparity there. And what is, yes, and so you can see that, essentially solar is creating the risk at the end of the day, and the wind is creating solar is creating the day risk in the middle of the day, daylight hours. Obviously, that's the only time it's active. And wind, there seems to be, at least on this day, a disparity in the wind production towards in the night. Maybe that's like more like 9 or 10 o'clock there. Okay, so that kind of syncs with obviously a quick look at the data. You could see that, but this is really putting numbers on which fuel is contributing what. Here is just another day, which is January. You have a similar sort of picture, except there is on this day there is a big wind contribution in the early hours after midnight, in the middle of the night, in this winter day. Okay, so there's it's failing to meet in some sense the pre-sunrise increase in load that starts maybe 5 o'clock or 6 o'clock or something like that. Okay, so I'm running out of time, so let me think what I should kind of close on. So, okay, so there is a methodology. I won't go into how from the solar you allocate it back to each of the things. And so this is all of the units. The x-axis is the midnight to midnight, 24 hours, and this is the allocation of the risk to each of the units. And essentially, the ones in the first 3 rows are solar, and so they're getting allocated the risk, during, the 11 a.m. to 2 p.m. Type region, and then on row 4, here the wind is, sometimes it has its response, and it distinguishes between the winds. So in other words, 309 wind 1 is some wind farm somewhere, and 317 wind 1 is some wind farm somewhere else. 309 is unreliable at night, and 317 is unreliable in the morning. So that's, important information, and the degree of unreliability is in the numbers. So this is really putting some measure of reliability on the individual assets, which is what we wanted to do. Okay, so I think this is 45 minutes, right, Tomoyuki? So I'll maybe take 2-3 minutes. Is that okay?
Sure, maybe you can explain more, maybe do.
Okay, I'll be interested if there are any questions or comments. Okay, so a lot of this, as I said, one of the people very involved is a professional software engineer, because we need to speed up this kind of stuff. So between, December and now, there was a speed up, from, so these are talking about 2 different grids. So now I'm going to talk about Texas 7K. And we can run the Monte Carlo simulations in 4 to 9 minutes. And let's say, I don't know, in September, maybe this was 85 minutes. And I still remember the program director of the funding agency was not impressed with 85 minutes. But, with effort, this is now down to 4 to 9 minutes, which is essentially what no one can do it faster than that, in a sense, because that's what it is. That's how Texas computer, etc. Okay, so with this reduction, what in serial time would be 36 hours of computing, or it would be 1.5 to 3 years of computing comes down to 36 hours. So we can run these things not in real time, but in terms of presentation over a weekend or something like that. And so this is, again, I think there's nothing particularly new I want to point out, but this is just to show you can do this on Texas. This is 7K, lots of different products. Here is the winter. So this was the summer histogram, very tight. This is the winter histogram, original and idealized, just showing you the version of this kind of thing. And then when you do the same thing, you break it up into cohorts, photovoltaic and wind in this case. Rooftop is not, I guess, so big, or it's not distinguished in this grid. Then again, you see that there is a the similar kind of pattern that you see. Solar is contributing, in this Texas thing, solar is contributing greater risk than wind, and there's a lot of volatility in the 7 p.m. hour as the sun starts going down and people are at home. Okay, this is December, and again, I won't go into it, but there's there's a different winter type pattern there. What else do I want to say? I think I've said that. Yeah, here. Okay, so here it is as a movie, so the clock is ticking in the bottom left. You can see this is putting for each unit what the CVAR allocation is. That's here. So you'll see the colors. Blue is a negative allocation, red is positive, and so okay. I think the colors are not okay. The colors are shown up here. Okay, that's not very dramatic. Maybe the next one will be better. Wait, that was May 27th. This is December 19th. Let's see if that's any better. I didn't really screen this before I put it in. Okay, so 1 p.m., 2 p.m., 3 p.m. You can see it's picking up in West Texas. Okay, I think this is because I put this into PowerPoint. That this is not. I think there's more to this picture than is showing up here. So let me skip that. The final thing. Okay, so I said, okay, renewables now in Texas. I don't know what it is, 10% or something like that. In places like California, New York, it's supposed to go to, I don't know, 30, 40%. And so, people are worrying about this now because it's going to get worse when you have greater renewables penetration. So what would happen in the futuristic grid? So people at Texas A&M and Wisconsin have produced a fictional grid, which has, how the grid might be for Texas 7K in 2030. So we're still working on that. I don't have that, but you could just ask, okay, like as a check, suppose I just jack up the number of renewables in the grids that we can run. And so hopefully we'll get to, what could happen by 2030 when if this prediction of what Texas might look like is anywhere near close. But in the meantime, let me just, do an experiment on what we can run very quickly, which is back to this RTS, which is, where so it's not just, you can't just sort of run a simulation by making up solars and wind, because you have to put it into the grid, and then there's transmission constraints and congestion and all this stuff that we don't really understand. And so it has to fit into the grid topology as we do it. So essentially what this is saying is that let's just, in the data that we have, the renewables have some capacity, let's increase that and decrease it from natural gas and coal, and see with greater renewables penetration what the effect of that is going to be. So, in the original grid, we reduced the thermals, natural gas, from 55 to 50%, increased the solar from 10 to 11, and the wind from 17 to 19. So not huge, not huge changes, but let's see the difference between these two things. And the difference is kind of dramatic. I mean, so the original grid is the gray, the light green is the more renewables, and where they overlap is this middle part is gray and green. And so you see that this is just the this is just the penetration rate, which is measured as how much they used, I guess, is I think I have that right. But what I want to show is probably this. Yeah, the average costs. This is over the 24-hour period of some day. Green is more renewables, gray is the original. And so you can see there is more load shedding. This is load shedding when there is more renewables, as you'd expect. The running costs are lower because renewables are not so expensive to run. And there's not much difference that you can see on the fixed costs here. Okay, again, we didn't change the renewables by that much. You know, here are the difference in costs. Let me see if I want to say anything else. So let me just see if I want to say, no, I think that's good. So yeah, so maybe I'll stop here. It's not, so you can see some, yeah, I think I want to say that the costs may decrease, but the tail risk is bigger. I'm just trying to find the picture which says that. No, it doesn't say that. Okay, so I think the conclusion with more renewables is that the cost may decrease on average because you're producing from a cheaper fuel source, but the tail risk obviously is greater and in a way that can be quantified. Okay, so I'm definitely out of time. Let me stop there and very interested in questions if there's any.
Thank you very much. Any questions from participants, panelists? Thank you very much for your talk, Ronnie. Very nice.
Ronnie, I have a question. So,
yeah.
so of course, allocating this total risk as you do, this is the right thing to do. But did you actually compare if you naively compute individual one and then sum them up versus the total risk? You know, total risk of the sum minus sum of the risks.
But I can't compute the individual ones because the risk is to the system. So I mean, if you just have one unit, it's not going to meet the demand. Like if you assume that there's no other production except one solar, right? Then that you can't run the grid on one thing. So everything is, you know, when it goes into the F, right, the optimization thing, everything is, is linked massively. So the bottom up, which is what I think you were saying, you know, can't be done. I mean, of course, in the statistical part, you have a distribution of its own production, you know, et cetera, but how that, you know, how you take an individual distribution, put it into the grid and get a aggregate distribution out, that is not doable. So the only way is to put them in, get the distribution of the aggregate, and then break it back down.
I see. Because, you know, I mean, the idea would be, you know, to see how much interconnectivity or dependency, if you want, between these two components is actually contributing. Because, you know, a risk of the total minus total of the risk, that's exactly how much dependence is between the components or whatever you are. But I understand what you're saying, that it's not really computable.
I think it's not computable. I can't think of a way in which you could do it asset by asset and bottom up essentially.
Yeah.
Thanks.
Sorry, this is Arvind speaking.
Okay.
Just to comment on that. In principle, one thing we could explore is summing over, like comparing what the sum of the first order allocations is to the overall risk, right? So the overall risk would be CVAR of the business as usual minus perfect world costs, right? And we can see how close it is when we just take the sum of, when we take I guess it would be the sum of the CVARs of the first order allocations for each unit. So I don't know off the top of my head if that'd be inherently meaningful, but that's a possibility.
So that may be something we can try.
Yeah. Because I mean, of course, I'm coming from, you know, asking this question like I'm still thinking naively as a portfolio and as a P&L. So, but this is really different. So, but very interesting. Yeah, thank you.
Thanks.
Pierre, do you have a question, please?
Yeah. Hey, Ronnie.
Hi.
How are you doing?
Good. How are you doing?
Thanks. So I want to come back to when you have the decomposition of your risk into phi's, and then you allocate the price of each phi's, the A's, right? You have the phi's and the A's.
Yeah.
Is there a way to, usually when we do a risk allocation like that, the A's are some form of expectation of the phi's under some risk neutral measure, let's say, and this is associated to a dual problem. Do you have that here? I mean, is it the same? The A's are some expectation of the phi's?
Yeah, so that's this formula. That's this formula on the top here.
Ah, okay.
So when you sum this, you get the expectation of the X conditional on X.
Yeah, but the expectation is always the same. It's not. That's my. The expectation is not under a different measure. Still the same measure.
Yeah, because nothing is priced here, right? So there's no.
Yeah, well, priced is.
I mean, in other words, you change the measure because you have to benchmark something that has a dollar value, right?
Not really. Simply, the pricing is done under the dual problem, and this is where this new measure will appear. So just a question, because this is what we were doing with systemic risk measure. That's exactly what we were doing. Oh, okay. That's why I'm asking.
Okay, no, I haven't thought about that, but I'll look at that paper. I know the paper. Yeah. Okay.
With C, I mean, because we're using CVAR, that could be interpreted as using a distortion risk measure, right? So there might be a connection through that.
I mean, yeah, I think maybe. Yeah. So probably the direction is that what JP is asking is, if you actually look at that extreme measure, then it turns out that it's exactly what you wrote here. It turns out this phi and this indicator is the Radon-Nikodym derivative with respect to the measure that you are looking at, the reference measure.
That may well be.
Right.
Thanks.
Yes.
I think, but again, I can point also out to where to precisely to look. So this indicator here is the new measure in the plus line.
Okay. So it's the X. Okay, that's interesting. But the dual, I don't know what the dual of this is. That may be. I mean, the Shapley value has a connection to some sort of games.
Yes.
And so obviously it was written as a number of players and so on. And I don't remember if they spoke about a dual. I mean, sorry, I didn't give any references here, but there is a paper by Dano. Igor also has a paper on this, many papers on this kind of thing. But yeah, we can go back and look and see if there's a concept of dual.
Next, Liam. Could you speak your question?
Yep. Can you hear me?
Mm-hmm.
Yes.
Yeah. So firstly, thank you for the talk. And my question is kind of about your model. I might have missed it, but do you assume that renewable energy is automatically consumed, or if there's a surplus of it, that it can be stored? Because the intuition there is, if we can store any surplus renewable, say, for instance, it's really windy in the middle of the night when the energy demand is low, that it would reduce kind of those tail risk values.
Yeah, so in the software, in the optimization grid model that was in this prescient software, they don't have, I believe, wind curtailment, right? So I mean, that's just not built in to their model.
No, they do. They
do. Oh, sorry. All right. So I knew there was a definitive answer, but I picked the wrong one. So they do have that in some way. So so in other words, not if wind overproduces, then it is curtailed. And storage. Okay. So I think maybe Arvind also you can answer this, but they have. I think the software, as far as we can tell, has some provision for storage, but the way the current running version is, it's not using that yet. So I think they have not. I think they've started developing, or had started developing incorporation of storage, but that's not there. But there is a sense that as renewables, goes to whatever in 2030, storage is not, the technology is not. I mean, it's debatable, but it's not going to be a full solution. I mean, it will help on them, somewhat, but unless battery technology improves, enormously. I don't know if that's going to match. I mean, I'm not an expert in that, but just from things I've read, are going to match what the projected renewables penetration is going to be. But the practical answer to your question is that, yeah, I mean, they are working on putting storage into it. So in some version later on, we expect to have storage.
Okay, thank you very much.
Thank you.